As we seek to determine if a series converges or diverges, we will add to the divergence test the integral test for another option. Here's the theorem. Suppose f of x is continuous, positive, and decreasing for all x greater than or equal to 1. Now, pause right there. These are the hypotheses of the theorem. So in order for the integral test to work, the function that we work with must satisfy all three of those conditions. It must be continuous, must be positive, and decreasing. So looking at the graph, the black line there is an example of a function that is continuous, positive, that is, it is above the x-axis, and it is decreasing. Now, we are going to associate this continuous function with the discrete terms of the series by examining the function for only integer inputs into that function. That is, let a sub k, the term of the series, be generated by the function value, again for integer only inputs for k, or let me be more specific, for all k in n positive integer or natural number inputs. So the graph again will help us to understand what's going on. If I simply take the natural numbers from the domain of f and determine the output or y value of that function, then those function values are going to be the same as the terms of the sequence. So notice here at x equals 1, the height of the function, the black function, is the same as the red dot, where the red dot represents the value of the series a sub 1. For integer input x equals 2, the value of the function, that is the y value or the height of that black curve, corresponds to the second term of the series. And this continues. I hope you didn't notice that your math teacher can't count. Let me fix that real quick. Okay, so when x equals 3, the function value f of 3 equals a of 3. So again, we're just saying the function value with natural number inputs is equal to the value of the series, so on and so forth. Now remember, we have already made this association between a continuous function and a discrete series when we were looking at finding the limit of a sequence. That same relationship will apply here between a continuous function and a series. So if those hypotheses are satisfied, then the sum from k equals 1 to infinity of a sub k, that is the infinite series, and the integral from 1 to infinity of f of x dx, the improper integral, either both converge or diverge. So let's get a visual of this from our graph. If I want to sum the series, I'm simply going to add the terms together. So I could visualize this as adding the y values of these functions with integer inputs together. I'm going to have an infinite number of those. Consider how that series relates to the integral. Technically, for the integral, think about your Riemann rectangles as their width decreases to 0 and you get an infinite number of those. You're actually adding every single possible y value together to determine that integral. So an integral actually sums more values than a series, right? The integral is summing a continuous function, whereas the series is summing discrete values. So if the integral converges, then the series, which is adding fewer values, should also converge. Conversely, if the integral diverges, then the corresponding series will also diverge. It's important to note that in the case of convergence, the value of the integral is not, in general, the value of the series. So when I calculate the integral, I am not necessarily obtaining the value of the series. I'm simply using the fact that if the integral converges or diverges, the series is going to follow likewise. So the good thing about this particular test is that it will allow you to connect all of your integration skills that you've worked so hard on with the new skill of examining series. Let's try example 2. Use the integral test to determine if the series converges or diverges. So example A, we have the sum from n equals 1 to infinity of 2 over 3n plus 5. So we're going to convert this to a continuous function. So when I go from discrete series to continuous function, I'm going to represent that by switching the variable to x. If we integrate this, we of course would need a u substitution. U could be equal to the denominator. Du then would be 3 dx. So 1/3 du will replace dx. So the pattern of our integral will be, let's move the 2 in front of the integral. We're going to have 1 over u times 1/3 du. Now this is a definite integral, but I've switched variables. I'm not going to update my limits. I'll come back and recover the original variable. So when we integrate, we're going to get 2/3 times the natural log of the absolute value of u, and we know this has to be evaluated. So to evaluate it, I'm going to go back and pick up my original variable and the original limits of integration. Now, one of those limits of integration is infinite. So this is an improper integral. We need to make it proper using our limit operator. So we'll do limit b approaching infinity of 2/3 times the natural log of the absolute value of 3x plus 5 from 1 to b. If we evaluate this from upper limit to lower limit, we'll have 2/3 times the natural log of the absolute value of 3b plus 5 minus 2/3 natural log 3 plus 5 will give us 8. As b approaches infinity, the natural log also approaches infinity. So the value of this integral is infinite. Now we could say that the corresponding series will behave in a similar manner. Making our conclusion, we can say by the integral test that cites the authority that we're using. And by the way, I forgot to verify the hypotheses. This is a continuous function. All terms are positive for x greater than or equal to 1, and it is decreasing. So the integral test applies. By the integral test, the series diverges because the corresponding integral diverges. So again, our conclusion is merely the fact that we know the series diverges because the integral does the same behavior. Let's consider example B. We want to find the integral from 1 to infinity of x over e to the x dx. Again, I'm going from index k, which is discrete, to variable x, which is continuous. To evaluate this integral, we can begin by making it proper using our limit operator, and let's rewrite it as x e to the negative x dx. Then it will be clear that we need to use integration by parts. So letting u be x, we see that du is dx. dv then is the leftovers, e to the negative x dx, and v would be e to the negative x divided by -1 or negative e to the negative x. So applying our integration by parts formula, I'm going to scoot to the left for a little bit of room here. We have the limit as b approaches infinity of u times v, that's going to be negative x e to the negative x. Now remember, this is a definite integral, so that will need to be evaluated, minus the integral of v du. Because v is negative, we can cancel this negative here, and we have e to the negative x dx. And again, that is a definite integral. As is usual with integration by parts, that second integral is pretty easy to evaluate. When we integrate e to the negative x, we get negative e to the negative x. Now we can run the whole thing from 1 to b. One thing that might be convenient for this limit is to factor out our GCF, negative e to the negative x, leaving behind x plus 1. So really we just have one term to deal with here. Let's plug in our upper and lower limits. Our upper limit is b, so we have negative e to the negative b times b plus 1, minus lower limit, which is negative, so we can make it positive, e to the negative 1 times 1 plus 1, which is 2. In attempting to calculate this limit, notice if b approaches infinity, our first factor here is approaching 0, while the second factor is approaching infinity. So we have an indeterminate form, but not the one that allows me to apply L'Hopital's rule. So if we go ahead and execute that negative exponent, we could write this as b plus 1 over negative e to the b. And of course, this second term here, let's just clean that up and call it 2 over e. Now, as b approaches infinity, we have our indeterminate form, infinity over infinity, which gives us the green light for L'Hopital's rule. So we have the limit as b approaches infinity. The derivative of the top with respect to b is 1, and the derivative of the bottom with respect to b is negative e to the b. And we're carrying along our second term here, 2 over e. Now we can evaluate the limit. As b approaches infinity, the denominator goes to infinity, causing the fraction to approach 0. Therefore, the value of the integral is 2 over e. What we're going to observe is that this is a finite number. That is, the integral converges. Because the integral converges, the corresponding series also converges. We could make our conclusion just like that. Because the integral converges, the corresponding series also converges, but not necessarily to 2 over e. The value of the integral is 2 over e. The value of the series is either the same or less than 2 over e. So our goal here is not to sum the series. We have achieved our goal of simply determining whether it converges or diverges. It's kind of nice to be integrating again, so let's try example C. We're going to go from series to integral. We'll rewrite this as the integral from 1 to infinity of arctangent of x divided by x squared plus 1 dx. Now this is an improper integral, so let's make it proper with our limit operator. Limit b approaching infinity of the integral from 1 to b of arctangent of x divided by x squared plus 1 dx. Now it looks like we're going to need a u substitution for this one. If you notice the relationship between the numerator and the denominator, if we let u be arctangent of x, then du is 1 over 1 plus x squared, or x squared plus 1 dx. So we'll be able to rewrite that integrand very simply as u du. Now if you'll recall, over here on example A, I made the choice to integrate in terms of u and then go back and recover my original variable so that I could make use of those original limits. That's one option. Here's the other option. As I move forward into this new variable u, I'm also going to update my limits of integration and just not look back to x. The relationship between u and x is by our substitution statement, u equals arctangent of x. So when x equals 1, arctangent of 1 is pi over 4. So my lower limit will change to pi over 4. So when we rewrite this in terms of x, the lower limit will be pi over 4. Our integrand is u du. Let's see what happens as x approaches infinity. As x approaches infinity, arctangent of x approaches pi over 2. Isn't that interesting? So we no longer have an improper integral. We've evaluated the limit moving from x to u, and now we have a definite integral. So let's carry it out. The antiderivative is 1/2 u squared, and we're going to run this from pi over 4 to pi over 2. Now, you don't even really have to go any further. You can see at this point we're going to get a finite value, and so we can go ahead and conclude this integral converges. Remember, that's all we're after. The value of the series and the value of the integral are not necessarily the same, but their behaviors are the same. So our conclusion is the series converges because the corresponding integral also converges. Now, the next problem is still an infinite series. Notice we're adding numbers together, and we have the ellipsis or the dot, dot, dot on the end, which indicates that this is an infinite series. But in order to apply the integral test, I'm going to need the nth term formula for the terms of that series. So if we notice the pattern of these numbers, the numerator is always 1. So when we write our series, sum from k equals 1 to infinity, we know the numerator is going to be a 1, but we want to express the denominator in terms of k. Now remember, the index indicates the position of that term in the series, so I'm just going to count the terms. K would be 1 for the first term, k is 2 for the second term, so on and so forth. So if you'll notice, if you square the position k and then add 1 to it, that's going to give you the denominator. For example, 1 squared plus 1 is going to give me 2. 2 squared, which is 4, plus 1 is 5. 3 squared, which is 9, plus 1 is 10. So we could write this as k squared plus 1. So we have expressed this series with the nth term, or in this case, the kth term formula. So we will analyze this in terms of its corresponding integral. Notice the function 1 over x squared plus 1 is positive, continuous, and decreasing. So this is an improper integral. We know we need to make it proper to be official. Hopefully you recognize the antiderivative quite easily at this point. That's going to be arc tangent of x from 1 to b. Let's finish it out. We'll plug in our upper limit, arc tangent of b, minus lower limit, arc tangent of 1. Now, arc tangent of 1 is equal to pi over 4. That's a finite value, so our concern is that first term. And we've seen this same limit many times over. It pops up quite a bit. The limit as b approaches infinity of arc tangent of b is pi over 2. Again, our concern is it finite or infinite, and in this case we get a finite value. Now, just in case I lost you on the limit as b approaches infinity of arc tangent of b, let me just remind you, knowing the graph of arc tangent is a huge help. You've got a couple of horizontal asymptotes, one at pi over 2 and one at negative pi over 2. And arc tangent of x looks something like this. So as x approaches infinity, the function levels out underneath that horizontal asymptote at pi over 2. But I know you already know that. What we're really interested in here is that the definite integral converges. So our series will have similar behavior. The series converges, but not necessarily to pi over 4. We can say the series converges because the corresponding integral converges. If we wanted to actually sum this series, we would have to develop a sequence of partial sums and then take the limit as k goes to infinity of that sequence of partial sums. That would give us the value to which this series converges. It may or may not be pi over 4. Now let's talk about a very famous and important series that has all kinds of interesting applications. It's called the Harmonic Series. The Harmonic Series, hold on, let me get my terminology right. Start with the sequence. The harmonic sequence is defined by 1 over n from n equals 1 to infinity. So we're dealing with a sequence, which means we're dealing with just a set or a pattern of numbers. So notice my sequence here is separated by commas. I'm just looking at the pattern of numbers. It's a very fundamental and simple sequence of numbers. You can see how that denominator progresses. Now, the harmonic series, so we're going from sequence to series, is given by the sum from k equals 1 to infinity of 1 over k. So oftentimes you'll see our particular textbook use n in association with sequences and k in association with series, but really you can use any index. Just notice that I'm going from a set or a pattern of numbers to the sum of those numbers as I proceed from sequence to series. Now this is called the harmonic sequence or the harmonic series because of its relationship to harmonies in music. If you're a musician, if you play an instrument, you probably have a really good understanding that there's a lot of ratios and patterns and interesting symbols that are used. Music is very algebraic. You may have not have thought about it that way before, but if you can read music, you're looking at the symbols on the page. Of course, there's time signatures and all that sort of thing, but you're looking at different notes represented with different symbols in different positions that represent not only rhythms, but notes, right? So you have a symbolic expression of music, which is really quite abstract. So you're taking this concept of music and coding it into a symbolic form on a piece of paper. And that's what we do with algebra. We observe some sort of relationship out there in the real world, and then we code it with variables and mathematical operations on paper. So in that way, music is also very algebraic. So that's why they say that musicians and mathematicians use their brain in a very similar way. So this harmonic sequence that we're looking at can be related to vibrating strings. Think about the strings on a guitar or maybe in the back of a piano, something like that. If I come and I pluck this string, so I'm going to pull it up, it's going to vibrate above and below its equilibrium position, right? So it's got different positions in time. Let's just say that the length of this string is 1. It's going to produce a particular tone. Now, if I take that string and I divide it at a node in the very center, and I pluck the string here, then the string's going to vibrate above and below its equilibrium position. The length of that string was half of the original string. Now, if I divide it into thirds, for example, and again, that's not exactly perfect, but I've got 1, 2, 3 sections. If again I pluck the string, it's going to vibrate above and below, and it's going to produce a different tone. And we could continue this division. That would divide it into 4 sections. Each time we pluck the string and cause that vibration, it produces a different tone. So these vibrating strings, whose lengths follow the pattern of the harmonic sequence, produce what's called harmonic tones. Now, the relationship between the harmonic sequence and the harmonic series is really quite interesting, and our integral test is going to help us to do this analysis. First question, does the harmonic sequence 1 over n from n equals 1 to infinity converge or diverge? Now, mathematics is going to teach you critical reading. We're talking about the harmonic sequence. How do I determine if a sequence converges or diverges? Very simply, I find the limit. The limit as n approaches infinity of 1 over n is equal to 0. We can say, therefore, because the limit is finite, the sequence converges. And it converges to 0. So if I continue writing term after term after term for the harmonic sequence, eventually those terms will converge to 0. So because the limit of the sequence is 0, the sequence converges. Example B, does the harmonic series, sum from k equals 1 to infinity of 1 over k, converge or diverge? Well, if I try the divergence test, remember the divergence test says find the limit of the term. If I found the limit of this term, I would discover it's 0. Remember, if the limit of the term of the series is 0, then your divergence test is inconclusive. It does not mean that the series converges, right? Divergence test says inconclusive. But we have another test that we could use now called the integral test. So we have an option. Let's try this option. Divergence test is inconclusive. What does the integral test say? So if we evaluate the integral from 1 to infinity of 1 over x dx, let's write this as the limit as b approaches infinity. Can we go ahead and integrate? I know you can handle this one. We get natural log of x from 1 to b. The limit as b approaches infinity of the natural log, we're dealing with all positive numbers here, so those absolute value bars can be dropped. Second term's the easy one, that's 0, but notice here the limit is infinity. So by the integral test, the series diverges. Because the corresponding integral diverges, the series diverges. So let's say, therefore, the series diverges because the corresponding integral diverges. So draw back out of these details and see the big picture. The sequence, the harmonic sequence, converges, and it converges to 0, and we know that because the limit at infinity is 0. However, the harmonic series diverges, and we know that because the corresponding integral diverges. So you have a divergent series based on a convergent sequence. That's pretty profound and interesting. All of this related to the tones that you produce from vibrating strings in music. Pretty interesting. Hope you enjoyed that.